Hi, good afternoon, everyone. Welcome to today's Emerging Technology webinar, Ring Gear Repaired with Dievar Material by Laser Powder Direct Energy Deposition. My name's Mary Ellen Doran, and I'm the Vice President of Emerging Technology at AGMA. This meeting is being taped, so for those on the live event, please put your questions right into the chat. For those of you listening on demand, please send any questions to me at Doran, D-O-R-A-N, @agma.org, and I'll work to get your answers from the presenters. This webinar series has been made possible by generous donations through our members. Special thanks today to Lee Bear, Vector Companies, Star SU, and Gleason. Thank you. Today's presenters are Igor Ortiz and Dr. Aaron Isaacson. Igor is an R&D project manager for special projects at XTAR, with over 15 years of expertise in product development, computer-aided engineering, computer-aided manufacturing, and production facilities. He holds an MSc in Industrial Engineering from CESI in France, and an MBA from the University of Barcelona. Aaron Isaacson is head of the Drivetrain Technology Center at the Applied Research Laboratory at Penn State University. Dr. Isaacson also serves as managing director of the Gear Research Institute. He holds BS and MS degrees in mechanical engineering, and he recently completed his doctorate in materials science and engineering with a research focus on functional design and optimization of high alloy steel microstructures for rotorcraft gears in loss of lubrication environments. Thanks very much for presenting today, and I'll turn it over to Igor.
Thank you, Mary Ellen. Good morning, good afternoon, and good night. So I'm going to introduce our repair case internally that has been done, a ring gear repair with Dievar material in an X-Flex machine tool from Exeter. So just a minute, sorry. So I have divided the presentation in three main areas. Who is Exeter? What is laser powder direct energy deposition, the process, and ring gear repair with Dievar material by laser metal deposition or laser powder direct energy deposition. So this is into group. We have different companies, but I'm going to focus just in two companies, Exeter and Ikergune. I belong both of them. Ikergune develops laser processes, laser powder direct energy deposition processes, systems and technology that is deployed to Exeter. They develop commission and design machine tools for, in this case, for laser powder direct energy deposition processes for specific parts. We are located in northern Spain, in Basque Country. We have three production facilities, two in a town called Elgoibar that are focused for subtractive processes or common machining, steel and aluminium parts. And we have a new production facility and laboratories specifically for laser powder direct energy deposition processes. We have a global presence. We have offices in Troy, Michigan, more than 35 years. We have office and service center in Mexico, in Germany, in India, and in China. And the dark blue dots are local partners in these countries that we work with. We have more than 1,100 machines sold. Also, we have 100 technicians, field technicians, and this is our worldwide network. Related to laser processes, Exeter develops three main areas in laser processes: laser hardening or surface heat treatment with dynamic variable spot shape and controlled energy density, laser cutting, and laser powder direct energy deposition, and laser cladding. So what is laser powder direct energy deposition? We use coaxial nozzles They are discrete nozzles, but we usually work with coaxial nozzles that are two nozzles that are assembled together. Blown powder is injected through the nozzles, and a laser beam melts the powder in a substrate. During the process, there is a heat affected zone and a dilution, but compared to traditional welding, the heat affected zone is small. Also, we can control with thermophysical powder material parameters the track width and height in different materials. In general, this process or technology is being used for surface improvements, wear resistant coatings, corrosion resistant coatings, and high temperature coatings, and also for repair processes, repair parts due to wear, repair parts due to corrosion, and high temperature coatings or parts that are working in high temperatures. Also, the technology can be used for near net shape manufacturing. For example, this 2D geometry that is done with a CAD model, or for freeform manufacturing. So we do a lot of research in powder quality characterization. We look different suppliers of powder, and also we check each supplier and each powder if it's a non-supplier, and we want to avoid porous in the powder, because in some materials like Inconel 718, these porous are reflected in the tracks, and even if we have good process parameters, the tracks and the part has porous, so the part is not suitable for entering service. We have researched different materials, and these are some of them. We research same material from different suppliers, and also we research same material, or when we check the quality of the supplier in different substrates, checking the dilution, no porous, lack of fusion, and that the quality is enough for the part itself. We have different powders under research, and also other industries, energy, aerospace, naval, and hypersonics can be suitable for additive manufacturing or laser powder DED. We have researched stainless steels, maraging steels, cobalt-based steels, nickel-based alloys, tool steels, B-materials, and also other high strength and specific powders, checking always the quality of the supplier and the process. We have own metallurgical laboratories, a specific team that research the powder, the quality, and the behavior with the laser. We check internally and also for projects and programs the quality that we achieve in our developments. And yeah, we have different tools and systems that we check the quality. How we do our research, or how we characterize the process, we start with simple tracks, selecting a specific powder. In this case, we have selected Dievar material for repairing the ring gear. We do different tracks with different process parameters. We check in each track in the metallographic laboratory there is no porous, lack of fusion, any issues in the quality of the tracks. When we have the height, also the width of the track, we select one track and the process parameters that are linked, and we launch one layer coating and 5 layers prism or near net shape geometry, and we check also the dilution, the porous, lack of fusion, cracks, and any issues that we can have in the one layer coating or the prism or several layer coatings. When we have checked the quality of the substrate with the powder in these three cases, we have a process recipe, and we save this process recipe internally and also to our laser software for toolpath programming. In parallel or after as built samples, we check also the as built samples, just a cross section, and we check the optical microscope and the same microscope if there is any crack, any lack of fusion, any can be a cross contamination of the powder, and also the porosity with the same microscope, how is the behavior of the powder with the laser parameters and all research that we are doing. So we have done 4 blocks of AC316L. From one hand, checking 24 hours non-stop processing with high power laser, and that we are capable of manufacturing, and the system is stable during 24 non-stop process. We have commissioned and the system works for long times. The optics, the cooling system, the laser source, the nozzles, every item that and tool that is involved in laser powder DED process. And in parallel, these 4 blocks, we have used them for taking samples for stress strain and also fatigue curves that we are taking in different materials. In this case, AC316L. So now I'm going to show two part samples that we have worked with in laser powder DED. One part is wind power main shaft repair, that in this case we have to preheat the material 42 chromolybdenum 4 to avoid cracks with the powder that is being cladded, in this case, Inconel 625. And if there is no preheating process, with 42 chromolybdenum 4, the material can achieve cracks during the process. Other type of part that we have repaired or we have developed the process for repairing with one of our customers is the internal repair of this conical pinion. And currently the different type of shafts and different type of conical pinions are come back to service as with the repair process. Our goal with Penn State University Gear Systems Institute, Aaron and his team, is to develop know-how on fatigue behavior of gears that are loaded with different loads, and to take this information. Our goal is to repair, coat, manufacture gears or gear teeth by laser powder direct energy deposition. In this case, this gears is an example of toolpath programming. Just that we are able that we can control the toolpaths, the powder and the material, and to build near net shape gear tooth geometries. And from Gear Research Institute, we are taking the fatigue curves in Dievar material. So this is our case. The case is an X-Flex machine tool from Echetar. This machine tool has 6 spindles. The part that has been broken, it's a geared ring that moves this spindle horizontally. So the gear ring was broken due to a shipment from a supplier. There were just 2 possibilities to manufacture a new ring gear or to repair by laser powder DED the damaged gear teeth. Internally, Echetar told us to repair by laser powder direct energy deposition. So we take the gear, because this gear or this matching tool has to be shipped to Germany in 3 weeks. So this is the damaged ring gear. It's I can't show the drawing, but the dimensions are between 700, 800 millimeters in diameter. This is a broken tooth that it has, for example, in the gears due to the shipment that has been broken. So to take the repair process with laser DED, we have previously studied the material behavior with Dievar, and also we have done some preparation, and we have been talks with Aaron if this root area can be not affected by the heat affected zone of the behavior of the heat that the laser input. So we have done some tests with the toolpaths, also with developing new process parameters with Dievar material. We have programmed the process parameters, or we have uploaded the process parameters in our software, and we have developed the repair process of the gear tooth with the toolpaths that previously were programmed. This is one tooth that has been repaired. We have been taking into account that not to affect minimally the root of the gear tooth, and these are some examples of the repaired gear tooth. The material that has been used is Dievar powder. It's a high strength steel. Why we have used this material is because, as I mentioned before, the powder comes without poros. It has a hardness between 52 and 58 Rockwell C. So high hardness for a gear tooth. And also in parallel, Aaron has taken the data of fatigue curves of the Dievar. So it's working well in different loads. And we have taken the measures of a sample of a whole manufactured gear tooth by laser powder direct energy deposition. As you can see, no lack of fusion, zero porosity. The small points represent the hardness in these areas. So we have done different analysis, not just the repair, just building sample tools. And finally, I can show you the repaired gear teeth and grinded gear teeth, because Exeter guys were in a hurry and they have to ship to Germany in 2 weeks this matching tool to commission it and to put it running manufacturing. So the gear ring is assembled in this area that moves this spindle head. And finally, it's assembled, it's commissioned, and it's running. I haven't got any phone calls, so I think that it's working. Yeah, I'm going to pass on. Feel free asking me any questions, any doubts. I am open, and yeah, I'm going to pass to Aaron the control.
Thanks so much. Are there any questions right now for Igor? You can feel free to unmute yourself if you'd like to ask him a direct question.
Mary Ellen, I'm sorry. There was one in the chat. If you'd like to read that off, I'm sorry for who I interrupted.
No, thank you. From Mike Z, what type of hardening method was the original part? Was it carburized, nitrided, or thorough
Carburized.
hardened?
Carburized.
Carburized.
The original ring gear was carburized. Yeah.
Mike Z, do you have a follow-up to that, or are you good?
My question would be, is there any kind of delineation between the material you added and the parent material? Do you see any kind of a transition or any kind of a spike in hardness in that area? Or
We can have spikes in that area, but in this case, or I can send you some specific more data with the substrates. If it's the same material, the spike is low or is higher. We can control the spike in the dilution area, preheating the part. In this case, it's not necessary. For example, in the wind power main shaft case, it's necessary because if we don't have a heat, if we don't do the preheating process, we can have spikes of high spikes in the dilution or in the dilution area between the melted powder and the substrate. So depends on the material, depends on the substrate. In this case, no. We have previously done these samples. If you can see the tracks that we characterize here, we characterize same material that we are going to work, same material of the geared ring, and also we coat with the Dievar material. So we check internally in our metallographic laboratory the hardness of course, in the substrate, in the dilution area, and in the Dievar that has been repaired. So we check the quality and the spikes, the hardness, if it's low or high spikes in the hardening. In the hardness, sorry. Make sense or no?
yes, it does. Do you have any section views of this completed product of that tooth, I should say?
I can, if you want, I can check, but I have a lot of tooth, another type of tooth like these ones that Aaron is going to show later. That are the Dievar. I can send you. It's public, but I haven't got this specific grinded ring repaired because the cheddar was in a hurry, and we have repaired it in one day, and the same day was grinded, and the next day was assembled in the machine tool. So in this particular case, I haven't got the photo. I have got just the assembly photo of the machine tool. But I have other photos of the process and also the sample tests that Aaron is doing at Penn State with Dievar.
Okay.
Thank you, Igor. Thank you, Mike. I know that contact information for Igor will be on the slide deck when it's sent out. Please feel free to reach out with more questions. We have a couple other questions in the chat. Was the repaired area ground or cut to restore the tooth form quality?
Grounded in the same job shop. That is a job shop that manufactures, repairs big gears. Yeah, it's one of our customers. Yeah.
Another question is, do you have a specification for the allowable amount of porosity in the powder?
Yeah, we have some specifications, but in general, I can send the data. I have to check with the lab, but we are seeing a lot of porosity in, for example, in the last batch, 17.4 pH, it's all 90% of porosity. So we have to be lower than 3% or maybe lower. There are some cases, some stainless steels that even it has porous, the trapped gas in the porous due to the laser, due to the to the laser process, the trapped gas can go outside. In other materials like Inconel 718, the trapped gas doesn't go outside. It stays in the track and creates a porous. So yeah, but in general, we try to avoid the porous, maybe 5%, or maybe lower. Depends on the material and the supplier. Yeah, that we have to check.
Great, thank you. Another question is, was the fractured surface processed before application? And
Sorry, can you
Was
repeat the
the-
question?
was the fracture surface processed before application? And I believe it's the same question as above where you said repair, but Dr. Glazer, if you have a follow-up question, please unmute yourself now.
I think I can clarify. I think they mean, was it machined or prepared in any way prior
Yeah.
to deposition?
Yeah, correct. Yeah, all the parts for repair process have to be prepared somehow. Small machining or maybe grinding have to be some way cleaned. In this case, we don't want to heal or clean a lot of the gear teeth. Just we clean some of the gear teeth. Minimum material, but yeah, some cleaning has been done.
Another question is, can the repair be done in situ, or must the parts be sent to a dedicated repair facility?
Technically can be done in situ. In our case, we do with our machine tools that is like a machine tool, like a milling machine that is in a job shop or a big facility, big production plant, and they manufacture repair parts. Technically, yeah, we can be a container can be designed, and a robot or a mobile machine tool can be designed for this container. Yet we haven't done this. We have questions about this, but we haven't done any project in this area. But technically, yes, can be possible.
Klaus asks, an example of a conical gear was shown. It
Yeah.
appeared that its bore was reworked. Was that the case? What powder material was used for that? And how was the bore machined to bring it back to specification?
Okay. So in that case, the conical gear, I have to check, but I think or have been used a Dievar or an AC420S for high harness. And when the clads are deposited, we have a stock material that is measured in a CMM machine for taking the measures, and later is assembled in a, we can say, a conventional 3/5-axis machine tool, and with a helical toolpath or with a boring tool, the part is remachined and it's taken to tolerance. We have a public video of a gearbox repair with the whole process. We have the repairing of the bearing areas with similar to this one, and also the pre-machining process of these bearing areas with the gearbox assembled, and the final milling operation that is a boring process for tight tolerances in these boring areas. So in general, is add material with good quality, and later measure this stock material and remachine, turn, mill, or grind it. Yeah.
Great. I'm going to save the next couple questions and let Aaron go, and we'll ask more questions at the end if that's okay with everyone.
I was hoping they would just keep
Yeah.
going so I didn't have to talk. Let me share my screen here. How's that look, everyone? We good?
That's great.
Okay. Okay, so I'm going to provide a bit of background, right, about ourselves and what we do here, and then we'll talk a little about what we did for Igor's company as well. So, yeah, my outline really is just to tell you a little bit about the Gear Research Institute for those of you that don't know us, and then we'll get into sort of. You can see here's an image of sort of conventional bending fatigue testing or single tooth bending fatigue, which is what we do a lot of. But in the case of additively manufactured gears, in one specific example, we needed to really tweak what we do to evaluate bending fatigue strength for AM parts. So I'll give you a little overview there, and then finally we'll get into some results with the Dievar gear teeth for that Igor was using for repair. Okay, so some background on GRI. You know, GRI is an independent nonprofit corporation that's managed by Penn State, the Applied Research Lab, and GRI has a board of trustees made up of folks from around the gear industry, appointed by AGMA, ASME, and also elected by the Gear Research membership. One of the things that really makes Gear Research attractive for both consortium and single client type research projects and testing efforts for companies is that we have a management agreement between GRI and Penn State that allows us to accept intellectual property and NDAs and things like that with companies that traditionally is difficult for universities, because universities like to own everything. So our mission really, again, it was established in the early 1980s to be a resource for the gear industry, right? Like, we want to provide a mechanism to cost effectively and quickly perform R&D and testing efforts that are maybe kind of on a middle scale, not necessarily full scale. You know, we don't have large, you know, helicopter drive system or wind turbine drive system test beds here, but we do have a lot of sort of, you know, between coupon and full scale type testing. We do a lot of, you'll see on my next slide, production part or component testing, but not necessarily full system testing. So again, we're a resource that's here to help drive new technologies forward. Part of our mission is to work with students. So if you have a need to hire students that know some things about gears, again, we don't have a lot of them. The ones that we do have are in high demand, but we try to offer opportunities for companies to fund and train students that they can potentially hire. Our focus areas really are not limited to these things, but it's anything involving power transmission or gearing or drive systems. We have never said no if somebody comes and asks for help trying to solve a problem in this area. So I like to say, from tractors to aerospace, really it's sort of, and even really beyond is our customer base. I kind of boiled down about 50 slides of what we do into one here. Again, it really comes down to conducting controlled gear failure testing, which there are a handful of folks that do that. But we try to work with our customers to meet their needs and adapt maybe one of our typical standard type tests to something which solves the problem cost effectively for the customer, right? So you'll see an example of that today with the AM testing. We've developed new types of testing for, you know, reversible bending fatigue testing, you know, for idler and planetary type gearing. We've done a lot of, I mentioned, production part testing, right, in cases where that's required. And that's one of the things that really sets us apart from other folks that do, you know, gear performance testing. Is if you want to test the bending fatigue of your spiral bevel gear out of your helicopter gearbox, we can do that. We can design test hardware and make sure you get the type of data you want. Yeah, so if there's anybody that has any more questions, feel free to reach out to me. I'm happy to tell you. Again, we do everything from sort of conceptualizing the test to, you know, failure analysis, metallurgical consultation, and things along that line. Okay, so enough about us. What we did for the Etatar group and Igor's groups were, I guess let me start a little earlier than that, right? So we started working with Igor, maybe, I don't know, maybe two and a half years ago. So, but prior to that, we did some work characterizing performance of additively manufactured gears. Don't let the first images here scare you too far, but we had a project back in 2017 where we were supposed to receive gears that look like the lower left here, right? This is a 3.5-inch diameter pitch diameter spur gear that we It's kind of one of our standard test gears for a lot of different things. We chose it because it was reasonably small with a narrow face width, so it would be low cost, low build time for an additive manufacturing evaluation project. The parts were very delayed. We came to within about 2 weeks of the project end date, and I got a call from a sponsor saying, we can't get you gears. All of our gears keep cracking during building, during cooling, during subsequent processing as we're trying to build them. And so what we've been able to do is build some teeth. And so what showed up were these bags of these very straight-sided single teeth. And they said, we want you to test these. And I'm not sure exactly what they thought, but we use a test fixture that I showed on an earlier slide for our single tooth bending fatigue testing that relies on an entire gear, right? So our loading arrangement looks something like this, right? The bits of the fixture are removed, but we're really applying a load and a reaction force to 2 different teeth, right? That we're applying, again, a controlled force to a point. And we rely on the gear body to sort of transmit forces and hold the part, right? So if you're just giving me this single-sided or straight-sided sort of rack tooth thing with no real reference surfaces on it, it's making our job a little more difficult. So what we did need a little bit of an extension, but we had to modify our test fixture and come up with a way to test this, right? So here you can see an as printed tooth form that we needed to test in bending fatigue. What we don't like about this, right, this straight-sided thing makes it difficult for us to apply a load using our standard tooling, which we like to keep simple, right? So on a normal single tooth bending fatigue test, we rely on the curvature of the gear tooth, the involute curvature, to give us I guess a nice elliptical sort of rectangular contact across the tooth. We contact it with a flat piece of tooling, right? So that we're using the curvature of the tooth to give us allow us simple tooling that's cheap and easy to make and easy to set up. We also like to have to actually compute bending stress, something that resembles a root fillet shape on a gear tooth, which here we don't necessarily quite have that, right? So if you compare this to a real gear tooth geometry, we have a bit more of of something that you can use an established calculation method to compute bending stress, where we don't necessarily have that over here. So our solution, which again, this goes back a couple years now, almost 10, was to take another gear geometry that we had testing tooling for the single tooth bending fatigue test and some experience with and create something that is more representative of a real gear, right? Like that allows us to load it with a similar methodology that we normally would, where we have curvature of the tooth, we have a root fillet geometry where we can compute that bending stress. And we also must establish some datum surfaces, right? So that we can locate and clamp and hold the part reliably that makes, minimize labor from changing the tooth each time. And so you can see this sort of cutaway of our fixture here, but our test sample that we use the shape of this blue highlighted part here, again, gives us not completely the next tooth over, but it gives us a root fillet geometry that is almost a full fillet, right? That allows us to compute bending strength, but it still allows us clearance without any real machining to go in and touch with our load application geometry here. Out near the tip of the tooth, but not completely at the tip, right? And so I'll show you a picture of the contact pattern shortly. And let's see, what else do I need to say? We're locating again off the bottom and the back surface here and then clamping down on the top to hold it tight to our fixture. What this small geometry does is it makes the AM folks that are producing these parts happy, right? They can make just the part that we're going to test. They don't have to print the full gear, keeps build time down, keeps powder consumption down. And it allows us to screen a lot of variables, right? Like as most of you probably know, with most additive processes, you can tweak a lot of knobs to change properties, right? Like you want to change powder, you want to change composition, you want to change powder flow rate, you want to change laser pulse rate, laser duty cycle, laser power. I mean, there's so many different things you can tweak. And so these folks not only have material, but they have all these other things that influence microstructure, residual stress, and so on and so forth. That again make it desirable to maybe only print a handful as a screening thing, right? Like let's print 5 or 6, test those, and then we can make more or make adjustments as needed. Okay, so now we're on to the project with Getzitar here to produce and measure, you know, bending fatigue performance of an alloy. And the real goal here is, you know, many people are building, printing metal parts, specifically gear teeth, right? But we don't really know what's the strength, right? Like what's the design allowable? How do we design a part? How big does it have to be to carry a load, right? We don't have that fatigue strength design allowable that we need. And so this is a kind of a start to that effort of like, let's develop a library to give us design allowables or some guidance to make real parts with these materials and these manufacturing methods. And so, and here's what Igor's company decided to do, right? They've done this 2 different ways, and he can answer questions about this of maybe which they prefer and why, but 2 different geometries of parts, right? So they build up a block of the Dievar material here, and you can see this one was more machining the teeth out, right? And then eventually cutting them off of this substrate. Then the next mode was there were some issues here with machining. I think there were some sharp edges, which if you saw, I remember in one of Igor's slides, he showed a cross section of a tooth that had sort of some very sharp edges in the root fillet, which wouldn't be good for fatigue. And so when I first saw those, we decided to change that before we tested them. And we actually utilized a wire cut, an EDM cut form for the geometry here. Again, this was sort of a first crack at this. How do we get these to work and see if we get good fatigue results from this? And this was the way to make it. And so you can see here the sort of form that was built up, and then they wire cut the entire piece from that along that the geometry that we provided, and then slice them up into the samples of the face width that we wanted for our fixturing. Bisque actually gave us really nice datum surfaces. We didn't have to do any surface grinding or anything like that afterward. Everything is true to the model, right? So we know that the reference surfaces and the tooth profile location are where we want them for accurately, repeatedly applying the same load to the same spot for our tests. I mentioned up here in my bullets, there were some concerns from some of a company that did metallographic or metallurgical analysis for Igor about some high levels of retained austenite in some of these parts. So we did do some testing of both as-built and cryo-treated parts with the goal of understanding whether there's any, you know, ability to convert retained austenite into martensite and improve hardness and reduce that. So I don't necessarily have good results for the cryo part to show you, but I do have some microstructure and some of the things labeled as built in cryo. So I thought I'd put that in there. And this is sort of an in-process report, right? So we're still continuing to do this, and you'll see probably the final results published in some sort of paper at some sort in the coming 6 months to year. Okay, so now we have parts made, right? So we've made our little single teeth or 1.5 teeth, whatever we want to call this little test specimen. And you can see here it's mounted in the fixture with our loading anvil removed, right? Typically, we'll put it in there, make sure everything looks good. It's sort of captured on the bottom and the backside and the top. The sides are not necessarily contacting. It's kind of sort of free to float in there from left to right. But again, we're supporting it on the bottom, and our loading is horizontal, right? So it can go left to right and not influence anything. We check our contact pattern, right? So here you can see most of the face width of a tooth. We'll put layout bluing on it while it's in the fixture, and then we'll apply a load, several cycles of load to make a pattern. And again, you can see what it looks like. Again, it's very much a line contact across, as you would expect from a flat, you know, piece of tooling contacting that. And we can use these measurements. Again, we can tweak it by shimming things up and down to control where it contacts, but we can take this number and put this into our bending stress calculation so we can, again, actually compute actual bending stress based upon the point we're applying the load. Let's see. So for the test, again, we're applying our sinusoidal load as we would in any sort of pulsator or single tooth bending fatigue test. Most of these are done at about 50 hertz. We use a stress reversal ratio or an R value of 0.1, which that's, you know, ratio of minimum to maximum load of 10%. And then our run out limit for this particular project, as most of our projects is 10 million cycles. Here you can see what a broken sample looks like, again, with the contact after a full test. That must have been one of the first ones with gluing on. And then this is one, that didn't fail or was a run out, right? So that's what we call a sample that exceeds 10 million cycles without cracking or without failure as a run out. Yeah, I think that's about all I have to say about that. Here's the data, right? So I have all of these are bending fatigue failures, right? I've presented this in terms of maximum applied load right now, not bending stress. That's coming, right? But what I need to do yet is to verify the root fillet radius and actually maybe even measure strain to make sure that this is sort of a new thing for us. I want to make sure before I publish or provide stress numbers that they're good and accurate, and that the root fillet geometry and radius and whatnot is exactly what I think it is. I also want to look and make sure, again, that the load application lines and the component going in is again correct. I want to make sure I give good data. So that's yet to be done. That will be done shortly. And once it's done, we're happy to share this data in a stress basis. And so what I can say, again, I realize pounds of force doesn't help folks a lot, but what we can say is, I'm going to show you some micro hardness and hardness data shortly, but that the data here is comparable to other things we've tested of this geometry of similar hardness, right? So it was surprising to me, it was surprising to Igor that when we first started that this material did as well as it did. And so we're encouraged by these results, that we're in the same load range for, wrought materials of the same hardness, which is in that middle to high 50s Rockwell C range. I'm also excited and surprised somewhat that the scatter looks similar to wrought materials, right? Even clean-ish wrought materials, right? Like this is this isn't surprising to see this kind of spread, from, between 50 and 100, 250,000 cycles or something like that at any of these given loads. We didn't do a lot of test points up here. This is going to continue. Again, we plan to produce additional sort of batches, if you will, to see if this is repetitive from, one batch to another. We plan to try some additional heat treatments as well and see if this can be improved, with added hardness or changes to microstructure. We're able to get runouts, right? Like sometimes with really dirty or materials with a lot of imperfections, it's difficult to get something to last 10 million cycles because you've got a lot of, if there's porosity in there, you've got a lot of fatigue initiation sites. And so some other AM things I've tested, that's been a case of like, you'll see that the finite life portion of your SN curve will tend to extend further and maybe even never hit a knee, right? Where you sort of transition towards an endurance limit. So again, we didn't run these beyond 10 million cycles, but that's for a traditional SN curve, you can envision, a finite life portion and then a knee and then a run out or an infinite life portion here too. So again, we'll perform some statistical analysis on this and try to create an SN curve as best we can with this data. We'll have some big error bands again, because we need a lot more testing to do. But this is better than what we had so far, which was nothing. So back to the test development, again, we have what we always do in any single tooth bending fatigue test program is look at our fracture surfaces. Initially, just quickly under light microscopy, again, these are SEM shots because I didn't have any light microscope images saved, to just say, hey, where's our fatigue origin sites? Do they look normal? And are they not at the edge break or the edge of the tooth, which would indicate a fixturing or load application problem, right? Like a twisting, or we're applying heavier load at one side versus the other. And here again, it's difficult to see, and you can sort of read the witness marks here and see that the origin site in this guy is over here somewhere, and this one's right here. Again, they're at or very near the surface in both of these cases, which is a good thing for the AM stuff. We're not necessarily seeing a lot of porosity or voids or anything like that in the material that's contributing to failure. So I would say in general, I was very skeptical, and I'm still impressed at how well this did. And it's not surprising to me to hear that a repair with this material if the heat affected zone challenge has been overcome, that the material itself in the as deposited condition is strong enough to carry some loads. So fracture analysis is going to continue there. I mentioned the differences in as built and cryo, right? This is a little bit difference in etch here, but really this is just to show that, you know, when we looked at the structure, you can really see, you know, wanted to see is crack path following I'll say a build, you know, difference in microstructure or one of these beads. And in some cases it does, but it's not necessarily in all cases. Here you can see it's kind of across these ones where it initiates, I believe. So these are loaded from the right flank here to the left, right? This is under tension. And so this one is a run out and did not crack. This one was a failure. And again, the crack initiated, I believe, over on this side. Again, I'd have to double check that, but I'm pretty confident that that's the way it was, unless this was reversed. But so this is being investigated as well. Again, more to come on this when we will put together a paper of some sort that really does this a little bit more thoroughly. We've done also micro hardness evaluation maps, right? So these are hardness maps that are created on our automated Vickers micro hardness tool that takes, I don't even know, probably 1,500 indents, 1,000 indents on each of these teeth, and then uses some creative MATLAB code to generate these sort of image plots that show the tooth and how the hardness varies. And you'll notice there's a little bit of a sort of a continuous or I don't know, perimeter around them, around the circumference there. That's sort of an artifact of how we're interpolating. But the data that's in the middle of these is real. There's very little variation, but there's some across there, but it's not aligned necessarily. You can't pick out like the layers, right, or the build passes. So that was interesting to me. The data's kind of shown down here. Again, we didn't do a lot of work with this. This was basically just to show, hey, where are we from a hardness and strength range? You know, we're in that middle 57 ish range in Rockwell C. Now, these are not post-process. This is as built, again, with the exception of the cryo treatment, which didn't really appear to change anything. So looking at the microstructure, I don't believe we did have a lot of retained austenite, but we'll again continue to look at that and higher magnification, and whether we do X-ray work to measure that, I'm not sure. That's really all I have. Again, that's the test method. I think we feel pretty good about it. We're getting failures that look like they should in bending fatigue. We've been able to do that with using the small little coupon that we've developed. It's more like a gear tooth than the folks that weren't gear people came up with, a straight-sided thing without a root fillet. And we're starting to build this, Dievar data set, and hope to understand that a bit more. But I think there's a lot of room for some cost-effective material property development for additional materials or other types of fabrication of the same material. So there's a lot yet to be done, but we're positioned well, I think, now to assist the industry with that. So okay, well, that's all I have. We'll take some questions if anyone has any.
Aaron, this is really terrific, and it's a long way coming. You've presented to our group for a while now, so this is really good information.
Thank you.
We have several questions to go over for both of you, so however you guys want to handle the questions is great. Our first is from Sapradeep. How do you generate path for DED deposition head in order to repair the gear?
We have developed our own software for laser processes. Started in laser hardening, and now we have developed for laser powder DED process. And the system mathematically controls the track overlap to have no lack of fusion between track overlaps and also in height. And in parallel, we save the process parameter data that we research in with a specific substrate and powder. So the software is for automated the repair processes. We can scan the part with reverse engineering, take the point cloud, and launch compare it with the nominal cut data, launch the toolpath. In this case, it's not necessary. We have mapped the points of the toolpath with teach mode of the customer robot cells in this case.
Thank you. Graham Loney asks about cost. So generally, how much does a repair like this cost, and is there an economic benefit to repairing multiple teeth versus replacement of the component if delivery is a non-issue? And I think he just wants general information.
For example, in gears, I can't tell you, but for example, in wind power main shaft, the cost of forging, machining, painting, measurement, wind power main shaft, the cost is between 120,000 euros, dollars, 150,000 euros, dollars. So a repair can be between 25, 40,000 euros, dollars in a wind power main shaft. In a gear teeth, in gears, we are taking fatigue data. So this is an internal issue that we have repaired, but we haven't got any machine yet repairing gear teeth. We have other machines that they are repairing wind power main shaft, they are repairing railway axles, and I know the cost in more or less in wind power. But currently we are taking fatigue data with Aaron to have this data, but we don't currently repair gears at the moment.
Igor,
Okay.
I have a question. So along
Okay.
the ideas of cost, it might give a better idea to talk about man hours, right? Like how long did that repair take? You said it was a day or two.
Yeah, in this case, it was a super urgent issue. Repaired. Well, we have the mail, shipped the part from our facilities in Elgoibar to a customer that we work very closely with them. And in the next day, we prepare the toolpath in the morning. We do the test of the toolpath with no laser, and in the afternoon, we launch the repair operation. And afternoon, night, they started grinding. Next day, ship it back to the assembly facility. And yeah, super urgent that the case of the gearbox case that has been repaired in same day and shipped to Australia next day. Yeah.
Yeah, that downtime is important.
Yeah.
Thank you for that. This is a good question, Aaron. Tony Catalanato asks, the gear is carburized, but the applied process is applying a solid material with a hardness of 58 to 62 Rockwell. Is the repair tooth now brittle due to being hard completely through?
With the research that Aaron has made in fatigue is not broken. I haven't no phone calls, so the machine is running. And the Dievar, we are surprised of the behavior in fatigue, even is not a specific material for gears, but we are seeing that the powders in additive manufacturing in laser powder DED process, they have different behavior, same material that is being manufactured from a casting on a forging. It has different properties, and also with laser parameters, we are seeing different metallographic qualities. Yeah.
Okay. We are at the top of the hour and we just have 2 questions left, which I'd like to ask. The first is from Carl Robato. How high was the retained austenite level prior to cryogenic treatment?
I think the answer to that is we don't know. They had Igor's company had some metallurgical analysis done by a company that was familiar with this alloy, and they suggested based upon either tensile, axial fatigue, or rotating beam, some other form of, or maybe some Sharpie testing, some sort of test results that they thought they could improve them if retained austenite could be reduced through thermal treatment. And so we kind of took that as a maybe they know, maybe they don't. And we had many of these teeth and thought that we could, again, determine whether there was possibility or high retained austenite by trying to force it to convert through cryotreatment and just test them and see, right? And there's another question that asked about, was there temper, right? So the next question from somebody there, William.
William
Yeah,
Banning,
about,
yeah.
no, we didn't temper them. We talked about it, but the goal was just
Yeah.
to see, is there retained austenite there? And if the samples got much more brittle because we transitioned a bunch of it to martensite, then we would know it was there, right? And then we would consider a temper process. But the idea was we literally just took one of them, put it in the cryo freezer for a while and tried it. And it didn't really change much. It actually performed a little better, but I think it was within the scatter band of the we only had 1 or 2 data points at that time. So we thought it was better, but upon a lot more testing, it really looks like it's shaking out about the same. So I'm not sure the cryogenic treatment did anything. So there's more room for improvement, but that's the issue, is right. We don't know what the levels of retained austenite were. And it might be, in fact, that it's quite low.
And then Aaron, I have one more question. Are you creating STLE files for people to be able to print the blanks? And what is the typical process that's used for printing the teeth that you do test?
I mean, I don't think there is a typical process. We've had them produced by powder bed fusion, and we've also had them done with DED. Again, most people are a block, like I showed in the pictures, a hunk of material and then cutting the teeth out, right? So we're make sure we get the geometry is important, right? We need to make sure that the load point and the root fillet radius are accurate. Unless you're going to produce 2 things of the same geometry and we just want to compare them, then maybe you'll get to say this one's much better than the other one. But so far, yes, we have we can give you whatever 3D model file form you want, and in the shape that we need, and you can print it out of whatever material you want.
Terrific. Well, Igor and Aaron, thank you so much for such an interesting topic and presentation today.
Thank you.
Thanks all of you for coming today. Please note that our next Emerging Tech webinar is Wednesday, March 5th, again at 1 o'clock Eastern. The AGMA Robotics Committee will have a panel discussing their latest white paper, which will be distributed at the same time, and it's on humanoid robots. It should be a very interesting topic, and that's available for you to sign up today on the AGMA website. This video will hopefully be available and on demand later today, first thing tomorrow, and we will make sure to send out the slides after this presentation to those who have registered for this event. If you're coming in through a link that you got from someone else, you can reach out to me at Doran, DORAN, @agma.org to get the slides. So thank you everyone for your time and have a great rest of your day.